A2 further maths, damped harmonic motion. Okay, so if you take a spring with a weight on it and you compress that spring, so you're pushing it up. Okay, you've seen this already, so you know what's going to happen if we let go of that spring. Then what we get is we get the spring oscillating either side of its equilibrium line, just there, continuously forever. And that's why because we're assuming that there's no other forces or energy loss acting on that particle on that spring. Okay, and that's where we've got simple harmonic motion from. But in reality, it's more likely that there are going to be other forces acting on it. Either forces that are potentially in the spring itself, maybe in the air around it, or whether you've got air resistance, all types of forces that would actually stop the spring keeping in simple harmonic motion, and it's more likely to slow it down and slow it down to the point where it reaches its equilibrium line. So we call this force a damping force. So the damping force is anything that slows that spring down and stops it keeping in simple harmonic motion. And what you find is that the damping force will try to reduce the motion of a spring back towards the equilibrium point. So what I'd like you to do is just keep an eye on the end of that spring, and I'll give you an example of what's going to happen if you have a damping force acting on the spring. Now last time it sort of bounced continuously either side equally. But the moment you have a damping force, this is the sort of motion that you get. So we can see that in that case, what happened is it bounced either side of the equilibrium line, and every single time it reached a point that was slightly lower than the previous one till it returned to the equilibrium point. Now that situation where it bounces either side, it still oscillates either side of the equilibrium point, is what we call light damping. Now, light damping does have an alternative name as well. Sometimes you might hear it referred to as under damping, and you've got to be aware of both of those names, sorry, light damping and under damping. Now, what you might have is if we actually ask you to plot the graph. So let's just watch that motion again, but this time let's just plot its position against time, just to get an idea of what the graph would look like. So we can see it goes down, reaches a point, and then continually oscillates either side till it returns to the equilibrium point. And we can see what I meant by that peak is getting reduced every single time it fluctuates either side of the equilibrium line. That peak is getting reduced further and further down because there is a damping force stopping it just oscillating like we saw before. Okay, so let's have a look back and look at a different situation. So I've squashed it in. I'm going to look at a damping force. Again, keep your eye on the end of the weight and watch what happens in this case. Now this time, because you can see, the spring is probably a more heavy duty spring. It's stopping it from just springing straight back up and down. It's returning to this sort of equilibrium point at a much slower rate. And what we noticed there is also that as it reduced back, it pushed it back gently towards the equilibrium point. It didn't oscillate either side. So what happens in this case is because it just tends straight back towards the equilibrium point, it's what's called a heavy damping. So a heavy damping reduces the weight straight back towards the equilibrium point. It does not cross the point at all, does not cross the equilibrium point. And heavy damping is sometimes called over damping. And again, you've got to be aware of both of those terms, heavy damping and over damping. Okay, so we're going to do one last one. Okay, so let's have a look at what the graph looks like for this particle. So as the particle last time it oscillated either side of the equilibrium point. Let's just watch the end of that line and plot its position against time in this case. As you can see, it slowly tends towards the equilibrium point. As it approaches the equilibrium point, its motion starts to slow down as it tends towards the equilibrium. Now, mathematically, it might never reach it, but clearly in real life, which you see, it does actually get back to the equilibrium point. So this type of motion just here might be because, like we said earlier on, or like I said earlier on, the spring is quite a heavy duty spring, but you might have a situation where it's the same spring that forms this sort of light oscillation, but you could put it in a different type of liquid. So you imagine if you had a very viscous liquid, if you were trying to do this in like syrup or treacle, and you let go of a spring, because it's actually powering through a more thick liquid as opposed to air or water, then what you might find is that that light spring in air becomes a heavy damping force because it's going in the liquid. So just be aware that it's not just the spring itself that changes the damping, it could also be the environment the spring is in as well. Okay, we're going to look at one last situation, and this is what's called critical damping. Now, critical damping is the point that's smack bang in between light damping and heavy damping. So you know that light damping sort of oscillates like that. It approaches that line really quickly, so quickly that it can't stop in time, so it passes it, and then it goes again, and then it goes again. And so what happens is you get that sort of pattern. Okay, it's oscillating. Heavy damping is so hard to move that it just takes its time and approaches it. Now, somewhere in between, it's gone fast enough, all right, fast enough to approach the exponential, the equilibrium point, but it doesn't pass it. So it's sort of cross between the light damping and the heavy damping. And we have a situation like this. So just watch the end of that weight, and we can see that in this situation, it just goes straight down towards that equilibrium point. And if we'd gone any faster, what would have happened is it would have passed it, and therefore it would have been light damping. And if it had gone any slower, it would have been that sort of situation, which was heavy damping. So critical damping is the point directly in between. Any faster and it'll pass it, any slower and it will be heavy damping. Okay, at this point, do you want to just grab your notebooks then, please? Title is Damped Harmonic Motion. And what we've just realised is that damping force that could act on the particle that slows the spring down is proportional to the velocity of the particle. So damping force is always proportional to the velocity of the particle. Now, what we know as well is that velocity can be measured as the change in displacement over the change in time. So we can write it as dx over dt. We also know, very much like friction, that damping force is always going to be sort of slowing us down. Like friction slows velocity down, damping force slows the velocity down in this case as well. And that means that damping force always acts in the opposite direction to what you're travelling in. So if you're travelling past the point of equilibrium going downwards, damping force is going to pull you back up towards the equilibrium point. So damping force is always acting in the opposite direction to the velocity. Now we can put these two together, or these three, because we know it's proportional. We got damping force is proportional to dx over dt. We also know it's going in the opposite direction, so it's going to be negative. And to change it into an equal sign, we can put in some constant. In this case, we'll call it constant C, capital C. So just pause there and make sure you've got down the information you need in your notebooks before you move on. Okay, so a particle that's moving under damped harmonic motion has two forces acting on it. Now the first force is to do with what we've seen earlier on with Hooke's law and simple harmonic motion, and that was the minus kx. So the force is always proportional to how far away it is from the equilibrium point. And that was the minus kx that we saw in previous lessons. But now we're also looking at, because it's damped harmonic motion, not just harmonic motion, what we're also looking at is this extra damping force. So there's two forces acting on the particle when it's attached to a spring. These two forces here. Now what we can do is we can put these forces together. So the total force is going to be the damped harmonic force, the damped force, which is there, and this force to do with how far away it is from the equilibrium point, the Hooke's law force. So we've got those two forces acting on our particle when we're in damped harmonic motion. Now we can use for F equals ma. We know that Newton's second law is F equals ma, and we can put this information in. So the forces are these two. The mass depends on the mass of the particle, and the acceleration we can write as d squared x over dt squared, or x double dot. So we can write our equation like that. With a little bit of rearranging, we get this very neat second order derivative. So we've got the acceleration plus whatever the constant is from before over m over the mass dx over dt. That's from the damped force. And then the km over x equals naught. So we've rearranged it and made it all positive. Now we know from previous lessons as well what k over m is. So if you check back in your notebooks and you have a look at what k over m is, we can see it was from the simple harmonic motion. And we know that we could write from this equation that k over m is the same as omega squared. So you might want to just go back over that previous lesson just to see the steps on where we got from simple harmonic motion to realizing that omega squared is the same as this k over m. All right, is the link between Hooke's law and simple harmonic motion. Okay, and the reason why I mention that is because we're going to just substitute that back in here. For exactly the same reason as we could do it when we're doing Hooke's law, we can do it here as well. Okay, so this leads to this second order differential equation. I've used lowercase c, which is the same as this constant here over mass. So that's got a connection with mass. Okay, and omega squared, which was the k over m, which we saw again in that previous lesson. But that is the second order differential equation that represents damped harmonic motion. And it's more likely that you're going to get down to these types of equations and have to use your second order differentiation equation skills to be able to solve it. Okay, again, just pause there, make sure you got down what you need in your notebook before you move on. Okay, so we're just going to carry on looking back at some of our previous work. We know from the auxiliary equation, right, that we can solve differential equations of this form. Right, so we can get an auxiliary equation from our second order differential equation, and that's going to allow us to solve the differential equation. So what we can do is we can link this just with that bit of work we just got. So the auxiliary equation for this damped harmonic motion equation can actually be written like this, all right, where I've substituted x in for an e value, okay, using exponentials, e to the kx. So I've substituted that in and I end up with this auxiliary equation here. Okay, and what that means is now I can actually go about and solve this, because what I end up with is if I look at the discriminant just there, it will tell me what type of solution I will end up having. So the types of solution I could have is if the discriminant is positive, if the discriminant equals 0, or if the discriminant is negative. And those three different answers determine what type of answer I'm going to get. So the value of this c squared minus 4 omega squared determines what type of solution I'm going to get to my second order derivative, but also what type of motion I get as well. Okay, so what we're going to do is we're going to look at that now. Okay, so just grab your notebooks again. Let's just put those two bits together. So we've got our second order derivative that we managed to form from damped harmonic motion, right, using the two forces from Hooke's law and damped motion. And we've put those together in our second order derivative. And now what we're doing is just linking that to a previous bit of work where we figured out the auxiliary equation by setting x equals to e to the kt. So when I do that, I can get this auxiliary equation just here. Now I know that can lead to three possible general solutions. So the three solutions I'm going to have, so just grab this table down in your notebook, that the discriminant can equal any of these three values. It could either be that it's positive, if I put it in the discriminant there. It could be that c squared minus 4 omega squared is equal to 0. Or of course it could be that it's negative. Now, there's nothing different between this and what you did before when you solve second order derivatives. So we know what the solutions of these are going to be. So the general solution for this one is when you can just put in ae to the alpha t plus be to the beta t. And you found your two k values and you can substitute both of those in, and it's no different. Doesn't make any difference that you're using it for damped harmonic motion. You still follow those same rules that you did when you applied the maths earlier on. So we can find the values of alpha and beta just there. Also, if it's equal to it, if the discriminant is equal to it, then what happens is we get alpha and beta being the same value. so we have to put this extra value, the extra part in. But notice a slight difference between this and what you did previously. So now, because we've got this C value just here, rather than using alpha, we can substitute in what that alpha value would actually be. And that means that when you come to your general solution, you're using some of the values you might have in the questions. This C value was to do with damped harmonic motion. Okay, it was the value in front of, it was the value that was in front of the dx over dt. All right, it was a capital C to start with, and we divided by mass. All right, so it allows you to start linking those together. Same with this bottom one. So this bottom one, normally what we'd use is we'd use the P and the Q, which are complex roots, the P there and the Q there. Now just be aware that we are still going to be doing that in this question, but we want to try to use this C squared and 4 omega squared. Okay, so what I'd like you to do, please, is just have a think. If that was your quadratic equation just there, what would the P and the Q values be in terms of omega and C? So I'm going to pause there. You can do this just in a rough piece of paper. You don't need to do it in your notebooks. Just have a go at using the quadratic formula and just see if you can figure out what the P and the Q values would be in terms of omega and C. Okay, so hopefully you just tried it in the quadratic formula. So there we go, K equals minus B plus or minus all over 2A. And you can see I've just separated them out already because I know it's going to be negative here. So I know it's going to be have I in it. So I've separated those two out. Now I've just expanded this part just here by taking out the minus. And I've done that on purpose because I know that I'm going to have a minus 1 in that square root. I know this is negative. I already know this is negative because this said it's negative. Okay, the discriminant. So I'll just take it out a minus there. And that's just allowed me to pull out this I value. And so therefore my two values for P and Q, one of them is minus C over 2, which is where that comes from. And the other one would be the square root of 4 omega squared minus C squared over 2. And that's where that one comes from. And the reason why I've just done that with you is so that when you actually look at these two answers just here, that one explains where the P value comes from. All right, because normally you'd have a P value there. You can see it there. All right, that's where that minus C over 2 comes from. And this one, which is alpha over 2, which is different to the Q, is because alpha is actually just that top value just there, where alpha is equal to the square root of 4 omega squared minus C squared. Now that formula you need to be using in this case. Okay, so that's slightly different. That's the biggest one that's majorly different from the other answer. Just being aware that the P and the Q are the same. They're just using them directly from the formula. Okay, pause if you just need more time to take any notes down there. Okay, so what's the type of dampening each one of these represent then? There's no surprises to the middle one because it's in between the other two. Okay, so there's no surprise on that one. Just making sure you get these two the right way around. So the first one is heavy damping. So if you've got a situation where you have a positive number for C squared minus 4 omega squared, then you get heavy damping. So you get that sort of shape. And yes, in your notebook, can we make sure we've got the shape of the graph drawn as well, please? All right. So in that situation, initially, we've got a velocity at 0, so maybe it's reached its maximum point just there, like we saw before. So it starts at 0, and it just approaches that line straight away. In this situation, because it's between heavy and no surprises light now down the bottom, this is going to be a critical dampening. Right, this is the one that just anything lower would go into that category, anything higher would be positive into that category. So equaling 0 is your critical damping. And the graph looks very similar to heavy damping, it just approaches it a lot quicker. Right, so a lot faster gradient just there. Okay, and the last one, as you could guess, is your light damping, and it's that sort of graph. So just pause there, make sure you've got a decent sketch of the graphs and the type of damping they are, because you need to recognise if it's real values, it's heavy damping, if it's negative values, it's light dampening, and if it's equal to naught, it's critical damping. All right, you need to know which one's which. So just pause there if you need it. Okay, so why don't we have a look at a question then and just see how we go about solving it. So I've got a weight of mass 5 kilograms and it's attached to a spring on a smooth horizontal table. So I'm attaching this weight on a smooth horizontal table. So think of the table across there. The spring is here, and I'm attaching a mass of 5 kilograms attached to it. I'm squashing it in slightly, so there is a tension in the spring during the motion. So there's a tension in the spring of minus 30x. So there's your Hooke's law. That's your simple harmonic motion. If there's no other forces, it would just be continuing at that all the time and doing nice oscillation. But there is another damping force. Maybe it's in type of liquid, or there's other forces acting on it we're not so sure about, but there's something that's damping the spring down. And you've got both of those. Now, a nice little hint to both of those is if you notice, one's in terms of x, one's in terms of v. So it's very easy to spot which one's the damping force, because that's always the one to do with velocity. This part of the equation, t equals when x and v, so that's going to help us probably find a particular solution later. And then finally, it's asking us to work out the x and the v in terms of t. So in other words, can you solve the second order derivative once we figure that out? Now, as always, if you've got forces mentioned in these types of questions, there's only one equation you should use, and that's F equals ma. We've got a mass, we've got some forces, we can use F equals ma to help us solve it. So the forces I've got are your minus 30x, your minus 25v, and that's going to equal your 5 times your acceleration. So I can put all that information in. Right? Rather than trying to remember the formula from before, you could just start from scratch every time and just put F equals ma. It's a lot easier. So you can put those all in. We could do a bit of rearranging, and we get down to that equation. Yeah, we could divide by 5, make it a little bit easier for us. And then, once I've divided by 5, I can find the auxiliary equation. So my auxiliary equation in this case is going to be k, because I've just divided by 5, plus 5k plus 6 equals 0. So a nice quadratic that we can solve. All those words and the stuff to figure out just boils down to this nice simple quadratic just here. Can I solve that quadratic? I hope so. Can you find the discriminant? Yes, it's positive, so therefore we get two answers. Alpha equals minus 2 and beta equals minus 3. So there's my two roots to my equation. And what I can do now is I can work out my general solution. My general solution is going to be x equals ae to the minus 2t plus be to the minus 3t. So I've managed to figure out the position of the particle at any given time x, and it will be given by that equation just there. All right, at any given time x, that's what it's going to look like. You can work out the velocity very easily from that then, because you could just differentiate acceleration, you could differentiate displacement to get velocity. So there we go. We've got our velocity equation, very similar indeed. As you can see, they're very closely linked. And so that one just there with the minus 2 and the minus 3 walk down to the front. Okay, so once I've got both of those, let's have a look at what this bit's asking us. Now we've got the general solutions, we can work out our particular solutions. So when t equals 0, x equals 1. So that's going to help us with that equation. And when t equals 0, v equals 2 will help us with that equation. So there we go. I got both of those. I can substitute them in. So I can substitute in the x and the 0. And I got both of those. I can substitute in the 0 and the v. And get both of those. And that will allow me to actually go about solving it now, however you want to do it. They're just simultaneous equations. So I end up with the correct answer at the end of x equals, a particular answer at the end I should say, of 5e to the minus 2t minus 4e to the minus 3t, and the same with the other one. Okay, so very well done if you followed that through and got the same answers. Okay, so just pause there if you need to. It's worth just having a look at the graph. So what I'd like you to do is just consider what the graph of that looks like. Be very careful how you start that graph as well. So just pause there, have a quick go at sketching it out. Okay, so hopefully you thought, well, if I look back at that table I just drew, this is one where it was positive, so therefore it was a heavy damping. So if you just drew it going straight down, I wouldn't blame you at all. But the one that was straight down, that we talked about before, had a velocity of 0, because it was literally when you let go of it and it had a velocity of 0, and then it went straight down. Now in this case, it has a velocity of 2. So initially, it's still going up a way, as if someone's whacked it and it's still moving up. Then what happens, it's going to reach a point and then it will come down. So we end up with this sort of situation. So to start with, when x equals 1, it was still going upwards. So it only went up for a little while longer, and then it came to rest. The velocity came to rest, and then it got pulled back towards the equilibrium point. So don't blame you if you had it starting there, because that's the only graph you've seen. Just have an awareness of the velocity. And you might also, if you'd started pushing it back, helping it along, you could sometimes get graphs that look like that. Okay? So just be aware at the start, the angle you're at, the gradient, makes sense because it's the displacement graph, the x graph, but the gradient you start at is always that one. So I'm starting with a gradient of 2. You can see that, going up with a gradient of 2. Okay, so just be aware of the graph and how you sketch it. And what type of dampening is that? Yes, it's definitely a heavy damping. It doesn't cross this equilibrium line just here. Okay, so what I'd like you to do is I'd like you to just have a look at this table. I'd like you to have a go at filling it in, please. So I've got 3 different weights. I've attached 3 independent springs, so they're completely different springs. We've got a tension force and a damping force, but sometimes they're missed out, so you have to figure those out. I would like you to make use of those to get the differential model and the general solution, and comment on the type of damping. Okay. Just beware that the mass of the spring, mass of the weights is 2 kilograms. So that 2 kilograms is the same for all of them, all of those weights. Okay, right. So I'd like you to I'm going to stop talking and pause. I want you to have a go at filling them in and seeing if you can get most of those boxes filled in. If you want some extra help, you're more than welcome to listen to me go through the first one. Okay, so if you want a little bit of extra help, let's have a look at this first one. So there's my 2 forces. I could use F equals ma and put those 2 in. Just be aware that what's going to happen is you are going to be dividing those by 2 when it comes to your differential model, okay, because your mass is 2. So I'll have 2 lots of acceleration, so therefore I'm going to have to half everything, which is why that should normally be 2 plus 6 lots of this one plus 4 lots of this one equals 0. But I can divide everything by 2 because it's a mass of 2. Once I've got that, I can solve it. So hopefully you solved it, you found a discriminant, and that led you to your answer. And much like the last one, this one here was a heavy damping. Okay, so I'm pausing there. I want you to see if you can go backwards. Okay, so let's see if you manage to go back then. So because I've started here, you might want to put the 2 in first of all. So that's 2 lots of that plus 4 plus 10x. We can take those to the other side and then we set up the F equals ma model. This will be your minus 4v and this will be your minus 10x. So minus 10x minus 4v because the mass was 2. But then once I got that, I could have gone this way straight away if I wanted to. I could solve that. Oh look, this time the general solution has got a negative discriminant, so therefore it looks more like this, okay, as your solution. So we've got this as our solution when I put in the correct values for the P and the Q. All right, even with all that stuff talking about how this is C over 2 and this could be alpha over 2 and all that sort of stuff, then you can still use your skills with solving differential equations, just getting the answer straight away. It is the same thing. You just got to have an awareness that these numbers in front, the coefficient in front of these, are linked to the C value and the alpha value. Okay, so we've got that. What does that mean then? What type of equation is it? This one's going to be a light damping because it was complex. And that leads on to the last one. Now we know it's critical. Now I know this is minus 12v. So really when I come to writing my second order derivative, I'm going to get d squared x over dt squared plus 6 dx over dt. But I don't know what the other part is because it's not given. But I do know something about critical damping. It means that the discriminant has to equal 0. So if I've got 3 dx over dt, that means, 6 dx over dt, because it's half of that. Because I've got 6, what's half of 6 is 3, so 3 times 3 will be 9. So let's put this equation on. So that equation just there is going to be a discriminant of 0. So one bit of information allowed me to work out the discriminant was 0. And then because I knew that was 9, that made that one minus 18. So very well done if you spotted that. I'm going to pause there and give you a chance to fill in this one. Okay, so this one comes from just knowing the root. The root was 3 like we just mentioned. So you got minus 3ta plus bt. And each of these would find the position of the particle for the at any given time for that motion on the spring. All right, whether it's bouncing up and down, or whether it's just approaching it straight away, or whether it's approaching it really quickly but not crossing the equilibrium line. Okay, so grab your notebooks. Let's have a look at the exam question on it, and then I'll give you some time to practice some. So a mass of 2 kilograms again is attached to an elastic spring. It's falling vertically. Now we haven't really looked at falling vertically because this is the first time that mass is coming into it. We've always had it set up on a table. So you've dropped this mass from the top. It's on a string, so to start with it's all just loose, and then at some point it's going to make that string taut, so that elasticated string. It's going to bounce further down, and then it's going to start doing that. So the best way to think about it is something like someone jumping out of a bridge on a bungee jump. All right, if they're a bungee jumper, they sort of bounce down, then back up, and so on. It's the same type of situation like this. You've got a weight, you've got an elastic spring attached to it, you've pushed it off the edge of the table, and it started to bounce once it becomes taut. All right. So I'm going to pause, give you a good opportunity to write down what you need. Feel free to have a go at it yourself. I'll tell you now that even if you could not do part A, you should still be able to do part B and C without even being able to do A. Okay, so let's have a quick look through and just get the information. Just be aware that if you can't do part A, you can go on and do part B. It's highly likely in your exam they will give you the second order derivative and expect you to solve it. The harder marks come from actually forming that second order derivative. Right, so what can I see? Well, I can certainly see I've got some forces here. Okay, so that's to do with air resistance. I can see there's tension here. That's your Hooke's law, 0.4x, to do with the distance away from the equilibrium point. What else have I got? Time traveled 0.6 meters. So I've got an initial velocity, looks like that. So initial velocity just there. I've got a mass of 2. What else? At time t, extension is big x meters. So at time t, then x is going to equal 0. I can see that because that's where it's just become taut. So that's going to be the equilibrium point. So x is going to be 0. Right, let's see if I can find this equation then. So my first thing I'll write down is F equals ma. All right, so Newton's law is F equals ma. Now the forces acting on it are going to be your damping force, and it's going to be your Hooke's law force. Right? But also in this question, we need to be careful because when we think about the forces acting on our particle, and this is why we haven't done anything vertically just yet. This particle has come down, the elastic has got taut, it carries on going down. What forces are acting on it? Well, yes, we're going to have the damping force acting on it, pulling it back towards the equilibrium mark. We're also going to have the part from Hooke's law to do with displacement, how far away it is. That dictates that number as well. So we've got those two. What's pulling downwards though is the weight. Okay, so that's the mass times the gravity. So you've got 2g pulling down. So before, when we had forces on a table going horizontally, we didn't have to worry about weight. We only worried about weight when it came to acting vertically. So what I can do now is I can actually put on all those forces. Okay, so I put those forces in and I've got minus 0.8v minus 0.4x plus the weight, the 2g, equals your mass times your acceleration. So what I can do now is I can change that into a differential equation. And I've changed it into this differential equation just here. I brought gravity in as 9.8, so that's where the 19.6 comes from. But I've also brought in the dx over dt and the second order derivative there for acceleration. A little bit of rearranging then. This is the new entity, the new bit, but we know how to deal with that. We just take it out to the other side because that is not connected to the x, the dx, or the d squared x. So we can bring that out to the other side, which gives us a slightly more complicated second order derivative because we're actually equaling a number, but it's not something we haven't dealt with before. Right, let's have a look. This is what I've got. This is what I'm supposed to show. So what I need to do is I just need to think about what I need to multiply by to get from there to there. The easy answer, of course, is looking at the number 2 to 5. So I'm definitely going to multiply it by 5 over 2. And if I do that, I end up getting the differential equation, which is exactly what I require. Okay, so just pause there before I move on and make sure you're happy. Okay, so what I'm going to look at now is I'm going to look at finding the x in terms t. And this is the bit I said you didn't have to be able to do the first bit. So if you couldn't figure out how to change all those words to that differential equation there, what you can still do is you can still solve it using the differentiation skills. So what I can do is I can find the auxiliary equation and therefore find my complementary solution. So I've got 5k x squared plus 2k plus 1 from this part. That's going to give me my solutions. This time I've got complex roots. So I've got minus 0.2 plus or minus 0.4i. So I've got those two. So this time I've got my complex roots. So what I can do is I can write out my complementary solution using those complex roots. So there we go. That's my complementary solution sorted. What I've noticed though is it doesn't equal 0 this time. So I need a particular integral as well. And of course, equaling 49 means it's a very easy particular integral, making x equal 49. If x equals 49, then that's going to go to 0, that's going to go to 0, so you get 49 equals 49. It's very easy to find a particular integral to this. So my particular integral is x equals 49, and that means now I can get my general solution. There we go. That would find me a general solution to this situation. But of course, I've got some extra information, haven't I? I've got this 0.6 I haven't used yet. I've also got the extension when t equals 0 that I can use. So that's what I'm going to do. I'm going to substitute in the two values. When t equals 0, x equals 0, because that's when the string became taut. That was the equilibrium point. It hasn't stretched yet at all. So I can use that value. And if I substitute that in, I can put that in. Notice, because this time it's cos and sine, one of those is going to cancel out nicely, leaving you a equals minus 49. So I can fill that in, and that's the a value now sorted. I'm still stuck with this b value though, but don't worry, we can use a 0.6 for the velocity and figure that one out. So I can put in when t equals 0, v equals 0.6. And that means that I can substitute it in, but don't forget you've got to actually calculate your v first of all. So you do have to do the differentiations. Just check you're happy with that. Differentiate the exponential, left that one alone, left the exponential alone, differentiated that part. So I've used product rule on it and got down to this. The 49 of course just disappears. That doesn't affect the velocity at all. And now that I've got that far, I can now substitute the two numbers in. Okay, so I'm substituting in t equals 0, and I'm also substituting v equals 0.6, and that leads to this equation. I'm sure you could do this yourself in your calculator, but you may as well cheat while you've got your notebooks. And I get b equals minus 23. So now I have a particular solution, because there is no unknowns in it, that links x and t. And that's what it's asking me to do. Find the x value in terms of t. So I'm going to pause there, give you an opportunity to take down what you need and check my maths as well. And that gives you your particular solution. Okay, so the last thing we're going to do is just find the value of t when the mass first comes instantaneously to rest. So think about what's happened. It's been dropped off the table. It's become taut. So that's our equilibrium. It carries on stretching, all right, further down, and then at some point it's going to start to bounce back up. Now this is talking about when it's bounced down and stopped its motion, and then it's going to go back up. So we're talking about when velocity first equals 0. So it's been dropped off the table, it's got a velocity. When it becomes taut, it's 0.6, and then it becomes 0 because it's slowing down with all those forces pulling it back up. Okay, so in that case then, it's going to be at rest when v equals 0. I've got my velocity equation from before, so I've still got that recorded. I'm going to set that equal to 0. And what I want to do is try solving this. So it's a bit of messing about, but I can see I can sort of cancel some things out, can't I? E to the minus 0.2t cannot equal 0. So I'm allowed to divide through by that. Okay. I can also multiply all these brackets out and get some sines and coses going on. So although it looks a bit nasty, we can certainly see that actually it's only some sine and some cos functions. So if I just simplify that down even more, I end up with this. 0.6 cos of 0.4t, sine of 0.4t. Now in that case, I can just divide by cos 0.4t, end up with a tan equation, and from there I can work out my t value. So again, pausing, giving you a chance to get down what you need before you have a go at some of these questions yourself. Okay, so just interestingly, it's worth having a look at the graphs. As I said before, this one, the red graph, is the position at any given time, given away from x, noticing that the equilibrium point, right, is a natural string length just there, is different. I said equilibrium point, and I do apologise, it's not the equilibrium point, that's the natural length of the elastic, is different to the equilibrium point, which was here. Okay, and you can see how, because it's light dampening, it sort of comes up and it oscillates either side until it approaches that equilibrium point, which is, no surprise, at 49. That's where the 49 came into it. All right, now usually on the table we have it at 0. We don't have an x distance away from the point. This one just here, you can see it's very difficult to notice. It looks like it starts at the origin. It doesn't. It starts off with a velocity of 0.6. It slows down to 0 at a time, and then once it slows down to 0, then it comes back down here. Okay, so it slows down and then it starts coming back. So it's gone here. It's still positive. So to start with, just to make sense of that, because I didn't do it very well. So it's got a speed of 0.6. It's still going faster and faster. Okay. Then what happens is as the forces start to act, they slow it down. It's still going faster though. It's just slowing down. It slows down to 0 and then it starts to speed up again, but in the opposite direction. So this is the first time velocity equals 0. You'll notice just there at about 7.7. So that's where it's got to 0. At the same point, you can see just here where the distance has reached its maximum distance away from its equilibrium point. And then it goes back and oscillates either side. Okay? But it's worth also making sure we look at those graphs and consider what the motion looks like. Right, what I'd like you to do, please, I'd like you to have a go at the exercises on 12C. Just so you're aware, these are the toughest questions you will face in your further maths. They are not straightforward questions, and you're not going to get anything more tricky now that you've finished your further maths, pure maths section. You've only got one more bit to go with coupled differential equations, which we'll do next lesson, and then you're finished. So stick with them, make sure you're asking for help if you need it, and good luck.